Today I'll present work on using energy-based models for resolving atomic resolution protein structures. I'm Yilun, and this is my first year at MIT, and I did this work as part of an internship at FAIR with Josh Meyer, Jerry Ma, Rob Fergus, and Alexander Rives. So when you look at the energy, when considering a protein folding, typically protein folds to the lowest possible energy given its sequence. So the diagram on the left shows the energy landscape of a protein as it folds. Given a good energy function, we may be able to both fold proteins and design them. So how do we learn this energy function? Traditionally, there have been three different approaches. One approach uses chemical force fields, which represent the physical forces in protein folding. Such approaches include AMBER, OPLS, and CHARM. A second approach uses statistical potentials using the Boltzmann distribution to represent on features fit from data. And a final approach, Rosetta, combines both of the previous approaches by both using molecular force fields, but also additional terms fit from data. In our work, we wish to build on the long history of statistical potentials to automatically learn both the features and the energy function directly from data. We take advantage of progress from generative modeling using energy-based models. So some background. A protein can be modeled as a kinematic chain with internal degrees of freedom representing angular degrees of freedom on both side chains and backbones. So on the diagram on the right, you can see that for the backbone degrees of angles, we have a phi, psi, and omega angles, which determine the overall structure of a protein. Simultaneously, we have chi1, chi2, and chi3 angle degrees of freedom, which determine the rotamer of amino acid, which can determine the energetic stability of the structure. These configurations are separated by high energetic barriers. For example, on the diagram on the right, you can see that the chi1 and chi2 valid regions is a very small proportion of the total space. And typically, to select between these possible conformations, you have to look at the surrounding molecular context. So for some background on energy-based models. Energy-based model is a distribution defined by energy function, specifically using the Boltzmann distribution, e to the negative energy. So we train our models to maximize the data likelihood. And to do that, we essentially, the likelihood consists of two different terms. One, the energy of the data point, and the second, the partition function. So first, we increase the likelihood of the data point by decreasing the energy of real data, while simultaneously sampling hallucinations from the model and increasing the energy of those samples to represent the partition function. This diagram shows an example of our training thing explicitly in the context of Rotamer recovery. In Rotamer recovery, we wish to determine the set of possible configuration angles discussed before of the side chains in the native context. To do this, we train our models to first taking the original conformation of the atoms, including the amino acid shown in green and the context shown in gray, and minimize that, while simultaneously generating a series of negative samples. These negative samples correspond to the hallucinations from before, and to generate them, we use the Denbrack Rotamer library, which samples a set of possible Rotamer angles given a backbone of the particular amino acid. The model architecture we use to fit this objective is a transformer architecture. We feed in minimal information of just the atomic coordinates, element type, and the ordinal information for every single atom in an amino acid. The transformer architecture allows us to do higher order reasoning by reasoning about interactions across all atoms in the molecule, unlike in a graph network where you can only reason to a few ones. A picture of the transformer architecture is shown on the right. Essentially, it consists of a attention layer followed by MLP repeated 6 times. Because of this, the architecture is further permutation invariant. We take the final pooling step of the transformer architecture and predict the energy from that. Our schematic of our training algorithm is shown below. Essentially, first we select a protein from the PDB database first filtered out for high-resolution proteins. We select a random amino acid inside this protein, and then generate a positive sample by determining the 64 nearest neighboring atoms to the carbon beta of the selected amino acid. We further generate n different negative samples, as discussed earlier, using the Dunbrack Rotamer library, and rotate the amino acid to the appropriate conformation. This gives us a set of both real conformations and a set of negative fake conformations. And we can train our model to contrastively decrease energy of real samples while increasing the energy of fake samples. Our model essentially per atom in the amino acid, we encode the position, the amino acid identity, the atom element type, and the ordinal label into a 256-dimensional vector per atom. Take the 64 atoms and apply the transformer architecture discussed before. So we evaluate our energy functions on the Rotamer recovery benchmark. This is a classic benchmark that has been used for a long time to benchmark the performance of energy functions. In particular, Lever-Fay evaluates Rosetta on this and uses this to propose additional terms to tune Rosetta. We evaluate on the same benchmark and test sequences and filter out using BLAST the sequences in the train that have substantial overlap with the test data set. We compare with a set of different neural network benchmarks. First, we compare with a fully connected network shown in turquoise. Then we compare with a set-to-set model shown in dark blue, and then our models shown in darker blue, and then finally with Rosetta in green. We find that our model is able to perform similar to that of Rosetta, obtaining approximately 75% performance similar to the transformer. We note that the two different Rosetta plots shows the performance of Rosetta between 3 years. So our model appears to be fairly similar to that in performance of Rosetta. We further evaluate the performance of our model per amino acid. We find in terms of Rotamer recovery that our model is able to get comparable accuracy to Rosetta on a wider variety of different amino acids. In particular, we find that our amino acid for charged amino acids such as aspartate, asparagine, glutamate, and glutamine perform better than Rosetta. While on other more common amino acids such as leucine, we find that our model performs worse. We further investigate the biochemical structure that is inside our model. To do this, we first consider the chi angle of different amino acids and then vary it to perturb it to different angles. In particular, the amino acids tyrosine, aspartate, and phenylalanine have a planar degree of freedom around the chi2 angle. We find that correspondingly in the red line that these amino acids have a low energy at both 0 degrees of perturbation and 180 degrees of perturbation. In contrast, all the other amino acids, which are shown in the dark blue line, have a minimum only at 0 degrees chi angle. Next, we further evaluated this on core and surface amino acids in the diagram in the left. Core amino acids are amino acids in the center of a protein and thus have more context. And we find indeed that core amino acids have a deeper energy wall than surface amino acids. We also evaluate the energy walls for different amino acids in the diagram on the right. We find that larger amino acids like tryptophan and tyrosine have steeper energy walls, while smaller ones such as serine and leucine have less steep energy walls. This is in line with the intuition that larger amino acids will have a smaller set of available conformations. Our model allows us to obtain a permutation invariant embedding for each possible molecular context, since our architecture overall is permutation invariant. Using this representation, we can visualize all the amino acids in both the surface and the core using a t-SNE plot. We find on the right that our model is able to, under this t-SNE plot, is able to separate the core and surface amino acids. We can also further visualize the saliency of our model. we overlay a hydrogen bond network onto a structure, and we in dashed lines. We then visualize the saliency of our model in red based off the gradient of the energy with respect to the input. We find that our model pays attention to the atoms that are in the hydrogen bond network. Overall, we've shown that energy-based models can approach the performance of state-of-the-art energy functions used in protein design when learned entirely from data. The model seems to respond in ways that correspond to intuitive understanding of the molecular energies. We believe future steps include combining with other existing energy functions and exploring combinatorial sidechain optimization and applications to inverse folding. Thank you. Sure. I think that the models have some issue with robustness, so I think they will still do something, but I don't think that it will match the performance we get here.
So there's obviously a lot of interest in intrinsically disordered domains these days. I guess they're not very well represented in these databases, but do you have any thoughts on whether those can, your approaches can be helpful there?
Yeah, potentially. So we do. So on a related note, we do notice some types of generalization that occur in our model. So it might be like in this intrinsically disordered domain, it might also have some show some unique insights.